The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so this is lecture 15. It's the last topic today and Friday, lectures 15 and 16, trusses within chapter 2, the last topic we'll do for discrete systems, and it's a lot of fun. Yeah. I wanted to say a few words first about last night's exam. Several words. First, overall, I'm sure it's going to be fine. The Ramis is grading the first two problems. He'll pass them to Peter for the next two, and I'll get them back. I'm pretty sure it'd be next week. I felt it was a fair exam, except I should have done a better job in connecting, in helping you with the matrix A, especially in problem 1. I'm glad that hint was there, the matrix A naught that goes with free to sort of say what kind of matrix to be looking for. And I thought I'd just repeat, make the connections that I should have made earlier. So just so we all see the point about these A's and the A naught and the A transpose A's. So if I take for that A naught, the free one, everybody sees that this is, and this connects, of course, with our graphs. Our graph is just this simple graph with, well, actually, is it 5 nodes? I guess there are 5. So, because as it stands, I have 1, 2, 3, 4, 5 columns. I've got 5 U's, U0, down U1, down to U4. And if I take A naught transpose A naught, that would be the free matrix. What size would it be, and what matrix would it be? Just if we do that multiplication, this is a first difference matrix. When I do A naught transpose A naught, I'll get one of our second difference matrices, so it'll be one of our special ones. Which special one would it be? B. It'll be the matrix B that has both ends free. And what size will it be? I guess it'll be 5 by 5, because I'm taking, that's right. That would be 5 by 4 times A naught, which is 4 by 5, so it'll be the 5 by 5 matrix B. Can I call it B5? Okay. So that was there as a hint. That isn't the correct matrix for problem 1, because problem 1 was fixed. Let's get there in 2 steps. Suppose it's fixed free. So suppose I make U naught equal 0. So I ground the top node, I support the top node. Oh no, shall I do U naught? Yeah, I'll do U naught. So that would knock out this one. If I say U naught if I fix U naught, say at 0 or whatever, now I've got the next A, I won't call it A naught anymore. Now 4 by 4, what matrix? Now if I do A transpose A, which of our special matrices am I going to get? T. It'll be T. It'll be the one that has the first, the 1 entry will only be a 1. So that'll be the fixed free matrix. It'll be of what size? 4. Now I've only got 4 unknowns, U1 to U4. Okay. That still is not what problem 1 is. Problem 1 was fixed. So as I did in the review, that would knock out both of these columns. So this now is the matrix that I was looking for in problem 1. And I wish I had made these steps, emphasized these steps in advance. I apologize. Okay, so what fixed, if without the C part in it, just focusing on the A, what fixed matrix would I get? Which one of our guys would it be? K of size 3. And while we're at it, what would be the story? How would I get one of these circular ones, which we haven't, which is sort of on our special list? For Fourier, it's the really special guy. So a circular one, I'm going to connect U4 back to U0. So I'm going to put these guys back in. And what else would change? If U4 was connected back to U0, now I'm aiming for this circulant, what matrix A is going to give me the circulant? So again, these guys are the A transpose A's. This over here was the A, and over here is the A transpose A. And now I want to fix A, and then I want to see the A transpose A. So suppose I give you that graph then. Oops, I should have. Well, just to keep this. Well, no, let me do it right. Connect the whole guy. So the fifth node coming back to the first. So that's my circle of nodes. It's a simple graph. What's the A circulant now? This would be the A for the circulant case. So it's got that back in. That shouldn't be erased. That shouldn't be erased. And what else has it got? What if I ask you for the incidence matrix? Now I'm in section 2.4, like I've given you a graph. Or you can think of masses and springs in a circle. So I've got 5 masses, 5 springs. What's my matrix A missing? It needs another row. It's got we just put in another edge. It needs another row. That edge went from the last node back to the first node. So we've got a fifth row. So you see, now it really is circulant. I would call this one also, I'd call that a circulant matrix. The diagonals are complete, are constant. That's what I and MATLAB and everybody else would call a tuplets matrix. And the command tuplets could create this. That diagonal is constant, that diagonal is constant, the other diagonals are constant. But more than that, what's additional here in the circulant, which is the thing that makes Fourier happy? The diagonal circles around. That diagonal is only got 4 entries in it, but it circles around sort of periodically to its fifth entry. So that's more than tuplets. It's circulant because it's coming around again. This we'll see in the discrete Fourier transform. It's really all good stuff. And now there's my A circulant. And what would be my A transpose circulant, A circulant? What would be A transpose A if I take that 5 by 5 matrix? C. Finally, I've created, so I've already got B, I've got T, I've got K, all those 3 special guys. And now the A transpose A for this circulant. So that's a first difference matrix for a periodic problem. And A transpose A will be a second difference matrix for a periodic problem, C5, I guess. It'll be 5. Okay, I hope that brings together if I was on the ball, I would have brought it together before the quiz. Can I just say a few words about the quiz and grades? They come out fine. Really, they do. I've been doing this a long time. And just, enjoy October. Don't I'm sorry to give you any exam at all, but it's, you know, it's a chance for you to show, yeah, I'm working on this stuff, I'm learning it. Everybody doesn't learn it first time. I don't learn it first time. Every time I teach the course, I learn something more. And if you're learning from this course, then I'm totally happy. And I believe that's the case, so I am entirely happy. And I hope the quiz, you know, some points of it were, I wish I'd prepared better, but I feel pretty good about it. I feel good about it, let me just say. Yeah, yeah. So, and I'm happy to have any comments, email or in person, but allow me to go forward with trusses. However, I'm ready always for a comment. Yeah, okay, okay. Anyway, enjoy trusses, enjoy life. Yeah, right, okay. And now, this should have been in the book, this page, so if it wasn't too late, I would like paste it in, because this connects A transpose A to my special matrices in the way I had in my mind, but I didn't put it on the board until just now, right? Okay, so I'll cover that up and ready to go with trusses. Okay, so trusses, we want to know what's the, you know, what's up. We want to get the setup right. Once we get the setup, we'll know what we're looking for. Okay, so a truss is a bunch of elastic bars with pin joints connecting them. Now, what do I mean by a pin joint? I mean that the bars can, stretching the bars takes force. Turning around the pin joint doesn't take force. So that the pin just lets them turn, but so we'll have forces in those bars. So it's like masses and springs, exactly like masses and springs, but yet we have a 2D problem. So it's a two-dimensional problem with masses and springs. And we could certainly have a 3D truss, but 2D makes all the important points. And then I can count the bars, 1, 2, 3, 4, 5. And I can count the nodes, happen to be 5 here. But now comes the moment. I have to tell you, what are the unknowns? What are the U's? Because of course, you know that I'm going to go from U's to E's to W's to forces, F. And you know that a matrix A is going to do that. A matrix C is going to do that. A matrix A transpose is going to do that. You're all ready. We need to know what's the setup. What are these matrices? Okay, and how many? So let me explain the setup. Typical node 1. We have forces in these bars. So that node 1 could have a force. We're in the plane. So we have a horizontal force and a vertical force. Together, that would give a force, produces a force in any direction, whatever. So this is the key point, that there's a horizontal force, F horizontal 1, the 1 being the force on node 1, but there's also a vertical force. And let me take horizontal to the right, positive to the right, vertical, positive upwards, just to have a convention. So how many F's have I got? Well, with 5, the point is I now have 2 per node. That's the difference. I have 2 per node, 2 forces. And I have 2 displacements per node, because that point there will be more forces. Some may be pulling this way, whatever. Maybe let's look at node 2. So node 2 could have a couple of forces on it, FH2 and FV2, and it moves like the other nodes. So now I'm introducing the unknowns. U is the movement. U, again, horizontal, And again, now we're talking about node 2. And it moves up, or doesn't, or moves down. But that's an unknown, u, a displacement, a vertical displacement of node 2. Do you see the setup? 2 forces per node, 2 displacements per node. So that is so that's like the number of unknowns is like doubled. And that produces an interesting situation. I've marked supports here. So let's just speak about supports. So what's happening at the supports? At the support, there's no movement. The whole that point is pinned. So this is telling me that u horizontal 5 is 0 and u vertical, sorry, that was 4. And it'll be the same for 5. U vertical 5 is 0. It's like grounding a node in the electrical case. We just see this pattern over and over, and we want to see, okay, what does it look like for trusses? So here's a support that fixes those. So those are not unknowns. And similarly, they're not unknowns there. Whoops, I'm still saying 5, and I mean 4. So those are boundary conditions, end conditions, whatever, and similarly here. So how many unknowns are there? If you now look at this picture, how many unknown displacements are there in this truss? 6. 6, right? 2 here, 2 here, 2 here, and none there. So the number of actual unknowns is 6. We could, my idea would be that it's twice the number of nodes minus the number of fixed things, reaction, whatever. That R would be 4 in this case. I've got 2 fixed here and 2 fixed here. So this would be 2 times 5, 10 possible displacements. But R counts the number of fixed displacements, 4, and leaves us with 6. Okay. So my matrix A will now be, it's always m by n. My matrix A will be 5 by 6. Okay, now you're going to ask, what is that matrix? But let me hold that off for a little moment. I wanted you to see its shape first. So you could now do this for a large truss, right? You count the bars, and you could count the nodes, and then you could count the unknown displacements, u. So u has, there are 6 u's. 6 u's here. And there are 5 e's. And there are 5 bar forces. And there are 6 equilibrium balanced force balances. 6, 6 for the node count, for the unknowns count, 5, 5 for the bars count. Okay, now, here's a point about this particular truss. It's not safe to get on it, right? And I want to say, why is it not safe? So this is a feature that comes into the truss question that makes it a little new and more interesting, little twist compared to the previous examples. That truss, I wouldn't stand on it. Now, why not? Okay, well, purely for linear algebra reasons, right? Of course. The matrix A is 5 by 6. So now what do we know about a matrix that's 5 by 6? So A is 5 by 6. 5 rows, as always, for the M. 6 columns, because now we have 6 unknowns. And what do I know about any 5 by 6 matrix? I want to ask about the equation AU equals 0. So I want to ask about it in linear algebra language, and then I want to ask about it in physical language. And the beauty is, the thing that makes trusses sort of fun, is these matrices A get pretty big fast. because when I put a few more nodes on, the book has a picture of a sort of tree house, then A is growing. And I don't all the time write down the matrix A. I haven't written it down here. What I've written down is just its size, because that's enough to tell us something about this set of equations AU equals 0. What's the story on AU equals 0? Well, of course it has the solution U equals 0, nothing moving. You know, if I have no displacement, if the U's are all 0, then I have no stretching. The E's are stretching, elongation as before. How far does the bar stretch? Okay, so if I have 0 U's and 0 E's, but what other possibility am I going to have here? I'm going to have probably one solution to this system that isn't 0. I'm probably going to have one set of displacements U. Yeah, look what's happening here. This is AU is the E. So I'm going to have this, I'm going to have at least one, and probably in this case it will be one. There will be one, the neat word for it is a mechanism. And what does that mean? A mechanism is a solution to AU equals 0. So that a mechanism is a movement of the bar. So it's going to be non-zero. The bars are going to move a little. The nodes are going to move a little. The nodes will move a little bit in this U, because it isn't 0. But the bars won't stretch. So that tells us we've got instability here. That, of course, that always, if there's a solution to that, that's always telling us that A transpose A is singular. So let me just put that A transpose A or A transpose CA, C couldn't save it, will be singular. It's like our free thing in being singular, but the picture doesn't look free, does it? It's got supports in here, just not good enough. And I believe that if you look at this truss, you could tell me, and you could draw a movement of that truss in which there is displacement, but no stretching. Let me ask you how to draw that. And I believe everybody understood why was there a solution? It was because we have 6 unknowns, and we only have 5 equations. So this was 5 equations. Anytime you have 5 equations with a 0 on the right-hand side, so 5 homogeneous equations, whatever you want to say, when it's 0 on the right, and 6 unknowns, 6 U's, then you're going to have solution. You can't help it. You've got that many degrees of freedom, you've only got that many constraints, there's going to be solution. Okay, tell me how to draw that. Let me put in the truss now. What's the solution? So this is the fun part in a particular example at the start. How could that move without stretching bars? Let me see. Oh yeah, what could happen? Yeah, what do you mean now? Who's going to move where? What's the movement here? And I want to draw it over there. So often you give the answer by drawing it as well as by telling me the 6 unknown U's. So what can happen at this thing? So you're going to say the truss could, these bars could turn a little. And you notice that word, a little. We're talking small displacements, small stretches all the time here. I'll show you why we're always making that linearity assumption. So we're just, or small assumption. Okay, those move a little. And what happens to that triangle at the top? It sort of just moves along, right? So that the picture you would draw would be that you started there, and it moved along a little. I'll make it a larger displacement than I really have in mind. These guys, of course, are here. So they come out, and the rest of the truss, the top of the truss, just kind of goes with it, goes with the flow. Is that would be the answer that I would be looking for to draw the mechanism. That would show it. And if I wanted to write down the U that goes with it, what would it be? Let me again number these guys. This is 1, 2, and this is 3. So what's going on? What are the displacements of nodes 1, 2, and 3? And I'll always write U1, horizontal before vertical. Can we make an agreement? So I want to know about the horizontal movement, then the vertical movement of node 1, then node 2, then node 3. So I'll have 6 numbers there. And what could I put in for those 6 numbers? So the horizontal, let me suppose that first guy, I'll put a 1. Really, that's a bigger number than I should put, but it's a convenient number. So I'll just take it to be 1, even though I really have in mind. Let's say that's 1 angstrom, or one tiny little person. Okay. So what about the rest? What's the vertical? Oh yeah, this is a key point here. What's the vertical movement? This movement to me is horizontal. I'm going to say that the vertical movement is 0 of node 1, just moves over. And node 2 does the same. And node 3 does the same. So that's my solution. 1, 0, 1, 0, 1, 0. That's a simple movement, a simple set of displacements. Thing moves to the right. And I have not written down the matrix A, but probably won't even do it until next time. But you'll see that when we do, the matrix A for this particular truss will have this particular U as a mechanism. In linear algebra, U is in the null space of A. AU is 0. That's all that means. Okay, you see more or less what's up. But now there's one little thing that may be bothering you, which is what? If I come back to the 0, 0, 0 there, you could correctly say, wait a minute, those bars, if those bars didn't stretch, if they just rotated as you told me to do, then this was a cross. It was mostly a cross, but a little bit down, right? And I'm saying no. I'm saying 0. Okay. So how do I get away with that? Right. Okay. So I'm saying in 18.085 it's a 0. Right. Okay. And why? All right. So this is like a little timeout. Just to focus in on, let me focus in on node 2. So here's the guy, here's the bottom node 4 so it used to be vertical up to 2. This was node 2 and this was number 4. And then it rotated a little to there, to this position. So it went, this angle, if this angle was, let's say, theta, then what is that actual position? So let's say the bar had length 1. This is the origin, 0, 0. This is the point 0, 1 above it, okay? And now, that's before it moved. Then it moved a little bit. It moved to an angle theta. What's the position of that bar, of that node? What's the new position of the node? And then we'll look at the difference and we'll see the movement U. displacement. So what is the, how far did it move? Is it, what's the x coordinate? How far did it go across? Let me, if I put in that line, you'll know. So the movement across was sine theta. Good, sine theta. And the movement down, well, I guess, yeah. So let's find its position, and then we'll take the difference. So what's the vertical new position for that guy? I guess it's, yeah, it moved across by sine theta and down by 1 minus cosine theta. Are you agreed with that? Because here's cosine theta right there. And here's the little bit it moved down. Okay. So that now these are exactly correct. Yeah, this is in the position sine theta cos theta, and the difference was the 1 minus cos theta. Okay. Now, so now here comes the key point. Approximately, sine theta is approximately, if theta is small, and now here comes the smallness, sine theta is approximately theta. Sine theta is approximately theta. And 1 minus cosine theta is approximately what? Now, this is the important point. So theta is like the first term. If I expand, the exact term would be theta minus theta cubed over 6, But I'm only keeping that term. And 1 minus cosine theta. Now, what's the formula for cos theta? This is like worth it's a 1, because of course cosine of 0 is 1. And then you subtract what? Theta squared over 2, and so on. And then plus theta fourth over 24, whatever. Okay. So the 1's cancel as we expect, and I'm getting theta squared over 2. And this, yeah, so here was theta to the first power. Theta cubed was, we didn't care, and we don't care about theta squared. So that's why it's 0, because it's a second order movement, right? If theta is small, as I'm going to assume, small displacements, theta squared would, if I allowed theta squared and cos theta in here, I'd have a nonlinear problem. And I don't want that, and I don't need it. I mean, finite elements, structures, bridges, whatever, your first hope and expectation and calculation is small theta, linear problem. So to a linear person, theta squared is 0. That's why those guys are 0. Okay. So that's an assumption we'll often see. So it kind of was, if you, yeah, there are two kinds of nonlinearity in structures and elasticity. One would be to allow this geometric nonlinearity. Theta's large displacements, theta large enough so that you can't neglect theta squared. That's a tough one. If you allow geometric nonlinearity in, as finite element codes have to do, if you, like Abacus is a code that does major finite element calculations, nonlinear ones. I mean, at the beginning they were studying what are the stresses on cables under the Atlantic. I mean, those are fascinating problems. Or I mentioned car crashes. I mean, car crashes, the geometry changes, you have big displacements. But we're talking here about the linear small displacement case. Okay, so we'll don't forget that part, that when the truss gets more complicated, the principle stays the same. That that we distinguish between the thetas that matter and the theta squareds that don't. Okay, so now what? Now I guess I'm ready to give you, to complete this picture a little more. Okay, so we've understood what's the idea of a mechanism. Oh, how could I prevent a mechanism? In other words, if I stood on this truss, the slightest bit of wind would crash it down, right? I mean, so that's unstable. That's an unstable truss. How could I make it stable? I mean, if you were designing this thing, what would you do? Add another edge. You'd stick in another bar. Maybe stick in a bar there. What would happen now? Would it now be stable? You'd have to answer that question. You couldn't just put in bars, whatever. You want to put bars that do the job. Okay, now how many bars? We've now got 6 bars. So M is now up to 6. The matrix A is 6 by 6 now, whatever that matrix may be. We have 6 bars, 6 displacements. We can hope that we now have a 6 by 6, well, we do have a 6 by 6 matrix, whatever it looks like. And we can hope that it's not singular. We can hope it's invertible. We can hope that that mechanism is killed, and you see it is killed. The 6 by 6, that truss is now stable. No mechanism there, right? I mean, again, I haven't written down the matrix, but I'm really calling for engineering intuition here, that this truss is now stable. And of course, I can make it even more stable by adding a 7th edge, a 7th bar. So when it was 6, I had square matrices, A transpose, and then C, and then A would have been square. Now I've got 7 bars, and so I've put in a 7th guy. M is now up to 7. My matrix A would now be 7 by 6. And there won't be any solution. The mechanism will be gone because I've now got, 7 equations, and still same 6 U's. So we begin to get a feel of, are there solutions? Not. What I'm saying is, I can't tell just from the count that A is not singular. I could have a lot of bars and still be unstable. Invent a truss for me, just because. How could you invent a truss that had, maybe it has 7 bars. With those 7 bars, those diagonal guys, that did it. That made it stable. Our eye tells us that before we do any linear algebra. Tell me a 7 by what a thing. Well, yeah. Okay. So here would be. Shall we support both of these? I'll start out the same. Okay. Now, yeah. How could I? Let's see. I haven't prepared. How could I get a whole lot of bars? Yeah. I might not get 7 by 6 exactly, but how could I have plenty of bars and still unstable? Well, I could add in, suppose I do this. Oh yeah, this is already, that's a good example. That's not stable, right? Okay, let's practice with that one. That's just my idea, and problems in the book just ask you to practice with things like that. Tell me the count first. What is M, the number of bars? 6. What is N, the number of unknowns? Little n, the number of unknowns. What's the shape of my matrix here? A is, it's got 6 bars, and how many unknowns? 8. 8, right? 2 here, 2, 2, 2, none here. 6 by 8. Okay, and how many mechanisms am I now expecting? Probably 2. Probably 2. There will be 2 independent mechanisms here. Can you tell me what they look like? Draw them. What would they look like? What would be two different things that could happen, could go wrong with that truss? You see it, right? This could turn, as in our example, with the top part moving with it. Or a second one possibility would be the top part goes and the bottom part stays. Or any combination. So the whole thing could go like that. That would be one, but that wouldn't be the only one, of course. So in other words, we have a two-dimensional space of mechanisms, and you could give me two different, and there are not just two guys, all their combinations are there. So this would have two mechanisms. And I could put in bars, of course, that would try to save it. Well, I could, how many bars, what's the minimum number of bars I absolutely need to make this thing stable again? 2. Well, now suppose I put in these 2 bars. Right? I've got enough bars. I've got an 8x8 matrix, but I haven't saved it, right? Because it still has that mechanism. So you can't assume that because the count is right, you've avoided mechanisms, because in that example you haven't. Okay, so that would be a case of square 8x8, but not good. The matrix still has, so as soon as I see there's a solution to AU equals 0, I know that A transpose A will be singular and unstable. Okay. Before I go to the framework, let's just do one more thing. Suppose I take away the supports. All right. Let me put in some bars, though. I'll put in some bars. Okay. Plenty of bars. You want another one? Okay. How many bars have I got? Lots. Right. Okay. Now the matrix A, what do you think about this? Are there solutions? You haven't even seen the matrix A, of course, but you've seen the truss. That's what matters. How many solutions? Are there solutions to AU equals 0? Are there ways that this truss could move without stretching? Are there ways that this truss could move without stretching? And what are they, and how many are there, and what name should we use? Okay, what are they? How could that move without stretching? Well, it's got no supports at all. It's just free out there in space. So it could move. How many ways could it move? 3. It could move, everybody could move this way, all ones on the horizontal guys. Everybody could move this way, all 6 ones on the vertical guys. There'd be 12 unknowns here. And it could also rotate. What would be the rotation? I'm not talking about this rotation. This could not happen. What could happen? What rotation could happen here for this? So there's a third rigid motion. Translation, and rotation around, well, take this one as an example. The whole thing could swing around this. That would be a motion. Well, now you're going to say, well, why didn't I swing it around that one? And of course it could. But what would be the deal? It would have to be, I'll only have 3 rigid, there are only 3 rigid motions, right, up, and around. So if you give me another one like around this one, then somehow it had to be a combination of those. I don't even want to think what combination it is. But there are 3 rigid motions. So I sort of distinguish mechanisms, this word mechanism. So that's where the truss deforms. In these and rigid motions, so I'll say plus, possibly, plus rigid motions, and rigid motions would be it doesn't deform internally, the whole thing moves. And this is, of course, what we get in the case of not enough supports. And this is what we get in the case of not enough bars. Yeah, so maybe it's worth separating those two. In the examples we do, we'll usually put in enough supports to kill the rigid motions, and then the question will be, are there some mechanisms? Okay, now I have to start on what this is. Well, it'll be just a very quick start, so that what I'll do at the beginning of Friday, so Friday's the other lecture on this topic, and then the homework will ask you to do some trusses in this section. It's probably section 2 point something, 2.7 maybe. Yeah, what's the matrix C? Last second question. What's the matrix C? What size is it? What size is the matrix C for our original problem? Or no. What size is C? Is C involving, if I know these numbers, what size is C? 5 by 5, M by M, right? C is that diagonal matrix, one entry for each bar. C is just C, has a C1, C2, C3, and this W equals CE is just Hooke's law in each bar. So simple. It gets there in the middle, just the way that C in the first exam problem popped in and other C's. That gets there in the middle, but it's very extremely simple. Okay, so the real attention is on A as usual, and that will come Friday morning.